Now on to part 6 of the Yang-Mills talk. Roughly, very roughly, here's the status in the 1960s. And again, I'm glossing over all kinds of details. If you're an expert, feel free to leave a mean comment, and then I'll delete it. It's not at all obvious that Yang-Mills-Higgs, this idea, is real. It had some interesting theoretical properties, but there were lots of interesting theories going around in the 60s, especially about strong and weak nuclear forces. Is there any use for this broken symmetry idea? I mean, it's really important that if it's broken symmetry, then what kind of symmetry is that? Does it leave any traces? And in fact, it does. Even though the symmetry is broken and the entire theory is not symmetrical in the way that the basic theory would propose, it does leave very important traces on what kinds of things can come out of the theory. And so here's another question that it turned out to answer. A real dilemma in the 1960s, one of the dilemmas, but a huge dilemma, was the particle zoo. There were many, many, many particles getting created in accelerators, and it was an ugly situation. It was incomprehensible. It was getting worse, and people desperately needed to figure out what was going on. And so here's this picture again. I don't know. I can't remember if this is from Wikipedia or not. It's a nice picture of a very small part of the particle zoo, and it kind of gives things away a little bit. I would have preferred just a huge list of dozens and dozens of random information, and that's really kind of what happened. They were getting lots and lots of particles, and not a great way to organize it. Here you can already see the start of some pictorial ways of organizing the particles. You've got Ks, you've got pi's, etas, these are neutrons, protons, you've got sigmas and x's, deltas, here's x's and omegas, and you can see that they're these pictures are starting to organize. There seem to be some patterns here. And so whenever you have a huge number of things, but they seem to have some patterns and properties, maybe what's going on is they're made of simpler pieces. Like in the story of chemistry, people discovered that the reason that what the world was made of was not millions of different random stuff. It's molecules made of atoms, and there aren't that many different kinds of atoms. So are the particles that they're seeing in the 60s made of simpler pieces? How to tell in what way they're made, how to tell what the pieces are and what their behaviors are? Well, you look for patterns in the particles you do have, the big zoo, and you get pictures like this that have these patterns. And guess what? Symmetry is the answer here. Gell-Mann and Zweig in 1964 introduced the idea of what are called quarks, fundamental constituents of things like protons and neutrons. And they proposed certain theories about how those should fit together. And what their observation was, the crucial observation, was that the patterns in the zoo of these what they're claiming are composite particles, not fundamental, they match patterns of how a certain symmetry group can act. So remember a while ago, maybe in the second part or something, I talked about symmetry and the distinction between a symmetry group, the fundamental formal properties and formal laws of like rotation, and how those act on something. And so it turns out that if you have this one symmetry group, which is called SU3, you could think of it as sort of a higher dimensional kind of rotation. If you have that one symmetry group, it can act in various different ways, and if you sort of look at the pieces of all those actions, you get pictures like this. And so that was their fundamental insight. So the pieces are falling into place. In the late 1960s, you've got Yang-Mills as a theoretical framework. You've got that circle kind of symmetry. Everybody gets a clock to explain electromagnetism. You've got SU2, which is really very similar to three-dimensional rotation to describe the weak force, and SU3 to describe the strong force. You've got the Higgs mechanism to give the masses. And again, this is not completely historical, but I want to actually finally give you the Mr. Hyde part of the story. There's major worries with infinities in the theory. There were other reasons that people were skeptical about these theories until about the earlier mid-70s. But one of the highlights I want to show you is the infinity story, because I want to show you the big problem, especially from a mathematician's point of view, with all of this stuff. It really appeared back in the 30s. Early quantum field theory, it was very quickly people discovered it was impossible to calculate exactly almost anything for quantum field theory. Well, physicists are used to that. There's lots of places where they have to approximate. And so here was the 1-minute summary of the idea that they used. You start with what's called a free field theory. You don't have any interactions between the particles. You have a bunch of particles, but they're just flying around and not interacting with each other. There's no forces. And so maybe you have photons, but they don't actually hit anything. They don't actually talk to the electrons. And so they can whiz on their way and the electrons, and they just never actually interact with each other. So you slowly turn on the interaction. You artificially reduce the strength of the interaction, and then you slowly turn it on to the right strength. And you look at what happens when you do that, and you get approximate answers. It's called perturbation theory. You should get approximate answers, and that's all you need as long as those answers are good enough to test, and they can tell different explanations apart and get a decent approximation. So here's the big problem. When they started to do that, they didn't get some sensible but approximate answer. They got infinity, and they got lots of infinities, and they got infinite numbers of infinities. It was horrible. One of the sources of that, I'll talk about very briefly about some of the sources. One source is what's called vacuum excitation. One way to think about that is, remember I said that the fundamental idea of quantum field theory is that everywhere in space is pervaded by these quantum fields, the photon field, the electron field, the quark field. And they seethe slightly everywhere. You can just kind of picture it as like the surface of an unquiet sea. The vibrations, again, like that standing wave picture from a while ago, the vibrations are never totally quiet. Quantum mechanics says that if you have something that can vibrate, it kind of has to vibrate a tiny bit all the time. Turns out that's the simplest one to deal with to some extent. You can kind of subtract out. It's so uniform and simple. You can kind of subtract it out. But lately, people have been thinking that maybe this has something to do with the mystery of dark energy, which is something just in the last 15 years people have discovered that there's this weird energy out there that's making the universe expand even faster and faster, it appears. And it seems it has some real similarities to this idea of a vacuum excitation in quantum mechanics. But it's still quite mysterious. Well, it turns out these infinities it was possible to deal with them. It's called renormalization. And Richard Feynman, I've already introduced the idea of a Feynman diagram. We'll see in a minute that we'll see this come up again. Schwinger, Tomonaga, Dyson, Bethe, those are the big players, but of course a lot of other people helped. They systematically, if mysteriously, removed the infinities in the calculation. And the mysterious part is, even to the originators of this, it was mysterious and pretty ad hoc. Turns out this is really where those Feynman diagrams came from. I talked about, in an ahistorical way, how you can think of fields as particles and particles as fields, and you can draw these Feynman diagrams. Where they really came up in the first way that were super useful is that they systematized enormously this complicated process of renormalization and organized the regularization process. But a mathematician's qualm with this is that, okay, that's great. You're doing all this work to get some finite answers, but it's still just for perturbation theory. It's still just approximate. And we'd like to actually have an exact answer without the infinities as well. So Feynman's explanation for this is, again, very much particle-based. That, let's go back to this diagram. I told you how you can think of this as if time's going up in this diagram, that an electron comes in from the right, and an electron comes in from the left going right, and from the right going left. And they exchange a photon, and that explains the repulsion of these electrons from each other. But as the photon is going, it can create an electron-positron pair. Well, it could have done it here. It could have done it here. This electron could have put another thing into this diagram. There could be another loop over here. There could be loops upon loops upon loops upon loops. You get all these complicated loopy diagrams. And you get a huge, huge number of places where you get infinities in the calculation. Because these particles are kind of able to do anything they want. And by creating virtual particles, creating and annihilating virtual particles. And the beauty of the Feynman story is that, yes, that's possible in these diagrams, but by using the diagrams, you can systematize how to get rid of those infinities. So let me give you a little primer on how do you get rid of infinities at a very, very basic level. The simplest example is calculating the speed of your car. So Calculating overall speed is very easy. If you're going to a city that's 60 miles away and it took you 1 hour, then on average, overall, it took you 60, you were going 60 miles an hour, a speed of 60 miles an hour. You take the distance traveled, divide by the time. That's the speed. But what about instantaneous speed? If you're actually driving in your car and you're looking at the speedometer, it's not measuring an overall speed. It's sort of trying to tell you, what is your speed right now? Well, is there a way to use this distance over time idea, which is the definition of overall speed? Is there a way to use that to calculate instantaneous speed? The problem is the natural thing you would do is you'd say, okay, I let my stopwatch run for exactly 0 hours. And of course, in that 0 hours, I didn't even let it run. I went 0 miles. 0 over 0 doesn't mean anything mathematically. So how do we deal with that? Well, what you do is you put in an arbitrary small cutoff. You let the stopwatch run for just a small amount of time, 1/1000th of an hour, 3.6 seconds, and you measure how far you go in that time. So let's say we're on a track and you have a very precise way of measuring how far you go. Suppose you discover that in that 1/1000th of an hour you go 0.0692 miles. If you divide that, well, it turns out dividing by 0.001 is pretty easy, just moves a decimal point. Looks like you're going 69.2 miles per hour. That's pretty cool, okay? But this is 3.6 whole seconds. That's actually a long time to let a stopwatch run, especially a modern, accurate stopwatch. Somebody could say, that's not really an instantaneous measurement. That's overall measurement still, but just over those 3.6 seconds. Okay, well, what if somebody else had a better stopwatch? What if they ran 1/10,000th of an hour? This is 1/10,000th of an hour. That's 0.36 seconds. 1/10 as much time. And they measure that you went just about a tenth as much distance, but they were being very careful, and it's not quite exactly the same. They measure 69.27 miles per hour. Somebody else comes along with a better stopwatch and goes a very short time, 1/100,000th of an hour. They look at how far you went, 0.0006929 miles. It looked like this isn't the 7 anymore, it's a 9. When they measure it with a finer stopwatch, they might get a slightly different answer for the speed, 69.29 miles per hour. All these numbers are not exactly equal, but they're close to each other. And if in any reasonable situation, if you hire people with finer and finer and finer stopwatches, these numbers are going to get closer and closer and closer to each other. They'll change less and less. They'll approach what's called a limit. There's going to be a trend in these numbers for the speeds, and it looks like the instantaneous speed you've got is about 69.3 miles per hour. So this is a fundamental idea in mathematics. It's the root idea of calculus, that you look at a table of better and better approximations. You choose an arbitrary cutoff, but then you let the cutoff go to 0, and you look at and see if there's some trend, some predicting, if you can predict the trend in these numbers. And that's really, and of course it's much more complicated, but that's the basic idea here. Renormalization in quantum field theory is a very, very, very complicated version of this process. Originally, it was very, very ad hoc as to how to do it. When things get complicated, there's a lot of choices you can make. In this situation, going back with the speed, this is pretty much the only reasonable thing to do. I guess you could do it in a more perverse way, but there's many ways to try to remove these infinities, much more complicated analogs of what I showed with the speed. Not really clear that they give the same answer before you actually try them out. Definitely no mathematical proofs for most of this kind of stuff. And in the late 60s, it was hard to tell if this would work outside quantum electrodynamics. There were some real big reasons to suspect that it shouldn't work. And so let me tell you, there's a multitude of theoretical ideas that had to come together to make this work. But let me just tell you about two of them that were both in the early 1970s. Gerard und Hooft proved that gauge theories, Yang-Mills theories, these things with local symmetry, they can be renormalized. Now I said proved, that's proved in a physicist's way. It's not really completely rigorous. But he basically showed very convincingly to the physics community that yes, these theories have nice enough properties that they're enough like quantum electrodynamics that you can do these renormalization procedures. That was a huge deal. Kenneth Wilson, coming from a rather different direction, he gave a really new understanding of the meaning of renormalization. Not just you can subtract out these infinities and regularize these infinities. in an ad hoc way, but there's actually more of a meaning to it. It's a much less ad hoc understanding of renormalization. And part of what comes out of that is the idea that the theory that you're using and the theory you need to renormalize might just be an effective theory that works at certain scales of distance and energy, and then it's built on top of an unknown higher energy theory, but you don't need to know the details of the higher energy theory. It's somewhat like the idea that if you're a biologist, you need to know certain things about chemistry, but you don't need to know all the details. You just need to know what does chemistry tell biological materials to do. And if you're a chemist, you need to know a certain amount about the interaction, the consequences of atomic physics for chemistry, but you don't need to know the details of nuclear physics. And if you're a nuclear physicist, maybe you don't need to know all the details of some hugely high energy theory where some energy that can smash apart the bits, the most fundamental bits of matter. And this is an idea that I think predates Wilson to some extent, but he made it actually very mathematical and precise. And so that gives a lot. It puts renormalization on a firmer footing. Trouble is, it's still not what a mathematician would call a completely rigorous demonstration of things. So also in the 1970s, great experimental vindication. You've got Gell-Mann and Zweig predicting things based on the particle zoo, and they predicted the existence of new particles, and those particles were found. It explained new phenomena that were found in the accelerators. With difficulty, you could calculate some precise numbers. And so in the early 70s, there was spectacular experimental success for these models, and it all came together to become the standard model of particle physics. Now let me just say a little bit about the mathematical side here, because I'm a mathematician, I'm coming at this from a mathematical point of view, even though most of why this is interesting is that it's about the real world, it's physics. What about the mathematical side? There was great progress in the 50s to 70s in understanding and codifying the underlying structure of quantum field theory. People came up with axioms, fundamental rules that they thought that these things should satisfy. For a while, the physicists were doing it separately and the mathematicians were doing it separately. They finally got to talk to one another again in the 70s. That was a very good thing. And also in the 70s, with a lot of difficulty, mathematicians proved that quantum field theory makes sense, that it really exists and it satisfies the right properties, these wonderful axioms, and you can really do it exactly, although you can't necessarily calculate it, but you at least prove it exists in up to 2 space dimensions. Oops, that's a problem. Okay, we live in 3 space dimensions. So there were major problems in pushing the progress further than what they had and pushing it into the world we really live in. Major problems by the late 1970s. As far as I can tell, coming at it from a non-specialist point of view, it seems like the progress more or less came to a standstill. There are certainly people working on this, but it was a huge slowdown in understanding this stuff. Those infinities that come up in the theory, physicists have ways to deal with them, but that's different from actually putting it on an absolute sound mathematical footing and proving that it really works. The symmetries, it's not clear. In some ways they help, in some ways they hinder the process. They tend to make the infinities kind of bigger and harder to deal with. And so, the fundamental question is, the physicists have these calculations that approximate things, and well enough often to compare with experiment, but what are they really approximating? Is there something underneath that satisfies the properties that people think, or is it really completely different? So the $1 million math problem here is to prove that Yang-Mills quantum field theory makes sense in 3 dimensions, physical 3 space dimensions, so 3 space and 1 time dimension, and prove that it has a few special crucial properties. You've got to actually have some sort of Yang-Mills quantum field theory that looks really like reality, as opposed to some toy model, which would be maybe easier to work with but wouldn't be real. And so there's a few crucial properties that we see physically from these theories, and for which physics has some non-rigorous derivations as to why the theory should produce this. And we want to really have a mathematical proof. Yes, this really exists. In other words, finally put quantum field theory on a sound mathematical footing. It's been around in some form for 80 plus years and has never ever really been on a sound mathematical footing in the usual sense. And that's a disturbing thing for mathematicians. So the question is, though, is it a disturbing thing for physicists? Not really. Not for most physicists, I think. There's many, many other things physicists have to worry about. So the specific $1 million problem that's in the Yang-Mills statement, in the statement of the clay math problem, it's not, to be honest, what physicists are absolutely most interested in. So it's kind of ironic. Of all the $1 million problems, in one way it's the most important because it's so fundamental. It's about the fundamental nature of the universe. But it is about taking it from a very mathematical point of view. And I would love to see this problem solved, but that's not to say that all physicists in the world would really care about it necessarily. But a context for this, though, a little larger than the specific millennium problem, is the interactions of quantum field theory and related ideas, like string theory, for example, with mathematics. They have been amazing, and especially for mathematics. They've transformed much of recent research in mathematics. And it hasn't been necessary to make all of the ideas of quantum field theory fully rigorous. It gives a bunch of hints and suggestions for constructions, and then mathematicians can take those and modify them into things that can be made rigorous without having to really prove that quantum field theory itself can be made fully rigorous. And that has really, really transformed a lot of modern mathematics and has led to major, major research. And so that's the good side of the interaction of quantum field theory with mathematics, even though there is this continuing annoyance that we'd like to make the real theory itself completely rigorous. And that's finally the end.